Okay, hello everybody. Um, Today is about anticonnective tilings. So this is not a technical term. This is a term that I've made up for this problem that I've been thinking about for a little while. Um, so just a little bit of background for what this problem is. We're talking about MNK games, which is a class of board games. The most commonly studied of which is gomoku or wuzuchi in Japanese and Chinese respectively. Basically, you just have to get five in a row. There are a bunch of different sort of variations of this game, but the idea is pretty much that you're trying to get five in a row of your color, either horizontally, vertically, or diagonally. Um, so that's that's an example of an MNK game. But more generally, what it is any game of width M, height N. So that's just the size of the board, and connection length K. Um, so like that's a class of games, but there's sort of a broader class surrounding that of games which have extra rules and conditions and things, such as Connect Four, for example. Um, in Connect Four, you're still trying to get four in a row on a 6x7 grid, but there's the added condition of gravity. And recently, a math YouTuber has been making videos about what's called, I guess, hexo is the official name for it now. It's like hexagonal grid MNK game with a connection length of 6. However, you have to make two moves in a row. So, like, each turn you get to place two pieces, which is very similar to Connect 6, which is a slightly older game, but still invented in, I think, the early 2000s, which is basically Gomoku, but like five in a row. However, you can place two pieces at a time. Also, the first player plays one piece. But that's not quite important yet. We're not quite going to get concerned with all the details of any of these particular games. Really, we're concerned with what I'm going to call an anti-connective tiling, which is a way of preventing anyone from winning on one of these boards. So, like, for example, what is the minimum density of pieces that you need to insert into a Connect 4 board in order to prevent either player from being, like, possibly being able to make a line of four? Um, and so, in order to make this question as general as possible, we're going to consider um, a case for each type of grid connectivity that I've kind of mentioned in these games up here. There's sort of like the 8 connective grids, which are the ones where like you have diagonals and horizontals and verticals. So, for example, Connect 6 or Connect 4 or 5 in a row. Um, so that's like represented here as, the neighbors of this cell being all of the 8 cells around it. So that's all of the ways that you can begin to make a line. There's also, that's called 8 connectivity. That's the fancy word for it. Um, this would be a four connective pattern. So, for example, if a game were to use that, it would just only be able to make vertical or horizontal lines, right? Diagonals wouldn't count. And like it might not be obvious at first, but a hexagonal grid can also be worked into this paradigm. Um, where like if we basically imagine our hexagonal board, but we skew it by like some I don't know how many degrees or what the measurement exactly would be, but you skew it by some angle. And if you do that, then you'll notice that these blue dots in the center of each hexagon are now like aligned orthogonally, such that there's now like vertical and horizontal grid lines, and also a line of connectivity along one diagonal. So in that sense, like this hexagonal grid would be like representable as a 6 connective like model, I guess, where you have like these four and also only one diagonal filled in. Does that make sense so far? Everybody get how we're formalizing the idea of like three different types of graphs: the hex graph, the hold on, let me click the general. I'm not even watching chat. Cool, makes sense. Yeah, so that way we can sort of just define the different types of graphs that we're talking about. And for this talk, we're only going to be talking about these three: 8 connectivity, 4 connectivity, and 6 connectivity. And I'm going to, for the sake of this talk, I'm going to call them orthogonal connectivity, hexagonal connectivity, and diagonal connectivity. Moore and von Neumann neighborhoods. Okay, good to know. I didn't know that. For this talk, I'm using this because I don't like the term of connectivity, because in the case of these games, connectivity can refer to the length of the segment that you're trying to create. So I'm going to be using these terms instead, just for the sake of this talk. So then the question becomes, all right, first of all, let's just think about infinite grids. I didn't write that explicitly. Oh yeah, I did. For an infinite two-dimensional grid with one of these connectivity types, what is the lowest density of cells that we can block or like pop out or somehow remove from the grid such that the complement contains no line of length k? So in other words, if one player, maybe if just one player were to fill in all of the remaining pieces, they still wouldn't be able to make a line. So I'm just going to define a little function here. So G being a grid type, either orthogonal, diagonal, or hexagonal, and K being the length of your connection that you're concerned with, the density of like that pair, or D of that pair, is defined as the minimal density possible of a pattern on that grid, a pattern of blocking cells which prevents K connection, a connection of length K. And so like that beckons out, what exactly is density? Anybody want to propose a definition? Yeah, exactly. Yeah, right. You're thinking along the right terms, because obviously density isn't precisely well defined yet. Because you can imagine like a definition of density where we, start to like count partial sums or something, but that it depends on the geometry of how you order your pieces. Although you said means as m and n tend to infinity. M and n are infinity. We're only considering infinite grids, to be clear. So like we're saying for an infinite two-dimensional grid, we're not even going to concern ourselves with finite grid cases. Like to be clear, Connect 4 is usually played on 7x6, and Gomoku is, I think, traditionally 15x15. But for the sake of this talk, we're only talking about genuinely infinite grids. 120 Cell says, but we can measure density in a finite region and then take the limit. Exactly. Yep. So that's how we'll define density in our case. So the density of a pattern is basically, we imagine like a circle of radius r growing out from the origin, and we consider the density of like the limit of the density as that radius r approaches infinity. And you can certainly imagine some cases in which that limit is not well defined, like if you have like, alternating rungs of increasing radius that have like, density 1 and then density 0 and then density 1 and then 0, and then, your limit doesn't exist. But of course, that would probably never happen in practice, and you would never actually want to make a pattern like that. That wouldn't be beneficial for solving this problem. So you certainly can come up with patterns that do have a defined density. Like an example of that would be a tiling. If we were to tile it with some like rectangular grid, then that would be necessarily the density of the entire infinite plane would be the same as the density of cells within that grid. The limit will at least be the same for all center points if it exists, so it's not so bad. What is a center point? The limit will at least be the same for all center points. Yeah. In practice, you would probably expect all regions locally to have the same density, like hand-wavily speaking. Yeah, if you say, yeah, correct. Yes, that is true. Yeah, depending on where you center the circle, it wouldn't change the density of the grid. You can come up with cases where the geometry of like what shape you choose, like circle as opposed to triangle as opposed to square, where that would either make the density like be defined or not be defined. I'll leave that as a question to the listener of constructing such a case. But anyway, that sort of defines our problem space. So we now have our work cut out for us. So we're concerned with all of the possible values of k. I've just made a table up to 10 here in these three with these three categories. So anybody want to take a stab? Anybody think they know a couple of values here or can solve a couple of sub-problems? Feel free to unmute.
Okay, equals 1 is obviously You need to fill the whole grid, so it's
Yeah, good. Okay.
1.
Right. If you don't have a density 1 tiling, that means that there is a missing piece. There's a missing cell, and that would be 1 connected, right? That would have a length of 1. So these have to be completely full. K equals 2 orthogonal should be 50%, says Violeta. And how do you get that exactly? Can you give me an example? Checkerboard. Yeah, perfect. Okay, checkerboard will do. Can you maybe even... Actually, first I'll do this slide and then I'll ask you a follow-up question. So we know that the density of, like, for any of these lines is going to be, it's going to have to be greater than or equal to 1 over the k value itself. And the reason for that is pretty simple, right? If we have any individual row, we don't even have to consider the whole pattern, but there has to be necessarily some row that has a density that is less than 1 over k. And if there is a row that has density less than 1 over k, then that also necessarily means that there's some length k segment within that row that doesn't have a blocker. So this gives us a nice lower bound for every value on this table. You can obviously see that works for all 3 of the different grid sizes, because each of them has the property that rows have to satisfy this density value, so that works for the whole grid. Okay, we're getting some values in chat. So k equals 2 orthogonal should be 50%. Yes, checkerboard works. So what Violeta just said means that 1/2 is also an upper bound here, which should bound orthogonal by 1/2 above and below. Okay, yes, yeah, you guys are getting K2 diagonal. K2 diagonal, yes, that's correct. K2 diagonal is 3/4. K2 hexagonal is 2/3. Yeah, those are all right. We'll get to all of these individual values momentarily. But anybody else think they can take another, like, a large swath instead of nitpicking like one individual value here? There's like a big chunk of this table that we can just pop right out.
I think orthogonal always gets the minimum.
Yeah.
You can do diagonals.
Yeah, exactly. So for 4 connectivity, or for the orthogonal cases rather, if, like, for example, if we're trying to do like a k equals 5 example, then we could just tile with this rectangle here. And this is sufficient because, like, each row will, like, is blocked and each column is blocked. So there's really no trick to be seen here. So that's, in fact, orthogonal is at most 1 over k by coloring x plus y multiples of k. Yeah. Sorry, I didn't read that in full, but yes, I think you got the idea. Yeah, so orthogonal is solved. This is easy, so we can just forget about that for the rest of the talk. So now the question becomes hexagonal and diagonal. There are some other large classes that we can pop out here, although it's not immediately as intuitive. Anybody have any guesses? Yeah, so by construction, we can sorry, this is supposed to say upper bounds. We made a lower bound already by the proof above, by this proof. But now we can make upper bounds via construction. Sorry, the slide is wrong. Anyone have any ideas of how we can knock out a good chunk of these? There's one rather simple argument that will knock 5 values off the table. Sorry, 4 values. I'll give it 3 seconds. Someone's typing. Okay. Oh, wait. What if you try x plus ny multiple of k? What grid type are we considering here? X plus ny multiple of k. Are we saying n is a multiple of k? Multiple of k for some other value of n. Axiomatic System says there are constructions like that if I recall correctly. What, have you seen this problem before? I wouldn't be surprised, honestly, but I also wasn't able to find much by Googling either. So all of this is I shouldn't say all, almost all of this is my work, with some from a couple of people from WebGoat Guy's Discord server. For example, if n equals 2, you get knights move diagonals. Yes, yeah, okay, yeah. Multiple of k. What is k? X plus n by multiple of k for some other value of n. Yeah, like I see how the knight move would correspond to like n equals 2, and like oh, I see, you're multiplying k times the entire like x plus ny vector. Gotcha. Yes. That is a good idea. Do you know of any specific cases in which that would work? In fact, you might be barking up the tree to solve a somewhat harder case that I was going to talk about later. I don't think that's quite the easiest chunk to solve. I'll go ahead and spoil it. So, in the case of odd hexagon grids, we can basically do a pattern like this. So, like, if you imagine just offsetting by, like, precisely half over, you would imagine this hexagon here would have an x inside of it. If you just go right in the middle and up one hexagon, then block there. We've now eliminated all of the horizontal crossings. We've also eliminated all of the crossings on this diagonal, because as you can see, each rung down, we are eliminating one diagonal from this grid. In fact, you can even see within the tiling itself, I believe every diagonal is blocked, like once you take into account wrapping. Does this make sense? Obviously, that wasn't like a complete proof that this is a sufficient pattern, but Asher says, is the orthogonal case the same as the non-attacking rooks problem? Yes, if you make a couple of assumptions. Like, for example, is the tiling necessarily the same size as K? And that will be a topic of discussion sooner or later. But like, because we're also trying to tile the plane with this. So like, depending on the size of your tiling and depending on some other things, it might not work out necessarily the same way that like the queen's problem works out, for example. Does this make sense though? Cool. Okay, so we can repeat this pattern for any odd hexagon pattern. Evens don't exactly work because you can't even like move into the middle of the inner blocks here and then move up one, because you would be landing on a hexagon and then like it would be an edge that's above that. So that at least roots out the odd values for the hexagons. So we now have those in white. Ooh, okay, I spoiled it. So I think this is where Violeta was going a minute ago with like basically knight moves. So I'll say, anybody have a solution for 8 connectivity, but for prime rectangle widths and heights? I'll give people 30 seconds to think about it. The knight's move grid shows D of diagonal and 5 is 1/5. Yes, correct. And 5 is indeed prime. And also I'm showing 7 here, and 7's prime, and this works also. So does this pattern extend to all primes? Question mark. I'll give it 10 more seconds. No proofs. It is a little tricky to work out the casework. I'll wait until folks stop typing. By the way, while everyone's typing, doesn't nice work? Yeah, but why? Can you prove it? It does work. By the way, so while people are working on this, I just want to say welcome to everybody who's new, because we have a whole bunch of new people today from the video last night. Maybe like 4 or 5 in here. And also, just to be clear, you are more than welcome to unmute if you want to. You don't have to. Doesn't nice because z
Yeah,
over
the thing is, if
Yeah.
you write the equation for a diagonal, you basically get like a linear equation, and all of those linear equations can be solved in like modulo p because p is prime.
I think that's right. Well, there are actually 2 edge cases. Can you think of them, or prove why they are, or
Oh yeah,
incorporate
the
them?
edge cases should be like when your equation basically just looks like something with a leading coefficient of 0, which I think is what happens when you take like n equals 1 or n equals -1 in the construction that I said earlier.
There are some more edge cases. Something 1 and 2 generate z over pz. So I'll just go through the proof that does not rely on any like linear algebra or fields or anything. So first of all, I mean, obviously we have each row in vertical having an at sign, but this only is true if the width is divisible by 2, because if we move over like you can imagine, if this 7th row isn't here, then if this is wrapping around on this left side, then you like land on the same row, and then you skip this entire, you land on the same column as the first piece, and then you skip this entire column, and so on and so forth. If width is indivisible by 2, correct? Yeah, good call. Yeah, this should be indivisible. Well, that's our first edge case. If the width is 2 itself, if the width is 2, then this does not work. So 2 is a prime, but 2 won't work. Each down right diagonal has an at. So you can rather clearly see this. I won't go ahead and prove it any more rigorously than just look at this diagonal and then look at this next diagonal. It necessarily has one moved over, and so on and so forth. And since this tile's just fine, that works. Each upright diagonal has an at, and this is a little bit more hard to see right off the bat. However, you'll notice that anytime you repeat this pattern, you'll always have an at sign here on the right side, which is like halfway down the board, or almost halfway down the board, up to some kind of off by 1 due to it being odd. So then you'll wrap around, and then there's this one here. And that piece will always be at the ceiling of width over 2, and that has to not be congruent to -1, 0, or 1 modulo the width. And that will always happen, meaning you're landing on a new like upright diagonal each time you go over and then shift down 4. And since that value is like co-prime to the width of the thing, you're always going to be like shifting over by an amount of like that is an amount of like upright rows that is co-prime to the amount of total upright rows. So long story short, 2 and 3 are the only prime numbers that don't satisfy these conditions, 2 not satisfying this one and 3 not satisfying this one. So this works for any primes that are greater than 3. And that gives us 5 and 7 in the case of this table. Did that make sense? Any questions there? Yeah,
Okay, so why Why is a prime condition necessary? I feel like it just doesn't need to be divisible by 2 or 3. Like, it could work for other primes. I mean, other composite numbers, as long as it's not divisible by 2 or 3.
I think you would have to change this. Like, you would have to change the proof. You could be right that it could generalize more. I'm not sure if it does, and maybe it does. But at least all this proof is going to show is that it has to be prime. I mean, you could show that the seal width over 2 has to be like some other number, or figure out like what exactly that is, or if it's congruent to the width itself. I didn't bother doing that. But yeah, you could definitely be right that 25 is workable. Anything coprime to 6. You might be right. Yeah, I don't know. If I guess try it out and see if you can prove it, and leave it in the chat or something. Okay, so a couple of people already called out the values for some small ones. So we have this k equals 2 for a hexagonal grid, which someone said earlier. I think it was 120 cell. Yeah, so this is an example of us having a density of 2/3. The red things being the blockers, not being the pieces. So this isolates every individual white hexagon here. Anybody have a proof that this is optimal? I have one on the next slide, but see if you can figure it out. It's worth thinking about.
If you have more than 1/3 of the grid filled in, then some 3-cell triangle has to have 2
Yes, bingo, exactly.
pieces that are necessarily matching.
Right. Okay, so that puts an upper bound here at 2/3. Just identifying the pattern, but to prove that is actually optimal, exactly as axiomatic system said. That was the proof that I found too, where each triplet here forms a clique. Like each triplet of each triangle here is a clique of all pieces touching each other. So in each of them, there has to be there has to be at most one cell that is not like blocked. And of course, that's exactly what we see in the pattern itself. You'll see this triangle. You can just overlay triangles, and each triangle will necessarily have exactly one white non-blocked hex. Cool. And as axiomatic system also has beat me to the punch, that this also works for 3/4 being optimal for the K2 diagonal, which someone else also found, I think, just by vibe guess earlier. So k equals 2 for the diagonal grid. You play the exact same game. You just imagine a 2x2 square being tiling the entire grid. You just break it all up into 2x2 squares. Each square is a clique under connectivity, so each square can only have one non-blocked cell. And that gives us, sorry, that's supposed to say 3/4, not 1/4. Oops. But that gives us 2/3 as a proven optimal value for hexagonal, and 3/4 for diagonal. Okay. So here's a conjecture, and I'll leave it for you guys to think about for a moment. Is there is it necessarily the case that there exists an optimal k by k square tiling for any grid or connection length? I know someone, at least, if you already know the answer, don't say it. Anyone have any? All right, I'm going to require that everyone in the talk just gives a thumbs up or thumbs down as to whether you believe this is true. I want to believe. Okay. Anyone else? Anyone want to say no? Feels like it should be true. I'm realizing now. Yeah, poll. I'm feeling more. It sounds like there's more trues. I guess we have 2 trues and 1 false, and then a lot of undecideds. Okay, yeah, poll. Good. Yeah, we're not considering multiple. So like what I'm suggesting here is like if there is a a tiling which is not k by k, yeah, if there's a tiling which is like if there's either a tiling which is not k by k or a non-tiling irregular pattern that has density d, then there necessarily is a k by k square tiling that has density of equal to or less than d. Okay, so it looks like we got 3 thumbs up and 2 thumbs down. Or sorry, 3 thumbs up and 1 thumbs down, depending on, I'm not sure if 120 cells still has both of the thumbs raised. It looks like the consensus is yes, this is probably true. All right, well, we're at 5-2 now. Gotcha. Okay, 5-2. So I'm realizing now that I put my slides in poor order because we actually just saw a case where this is not the case. So for hexagonal, we had 2/3, which is a counterexample already that we've hit. Because this is not a square tiling, right? If you square tile a 4x4 grid here, then you'll end up with either collisions or like a suboptimally dense pattern, because like you're only going to be able to get like dyadic numbers, for example, by doing that, or things that are like divisible by 4, I guess to put it more simply. So you're never going to hit 2/3, which we already proved is optimal. So okay, well that's a counterexample, but what about other cases? And yeah, oof, yeah. So I may have misread the conjecture. I'll give it a little bit more thinking time. My argument was you can just block every cell which gives an upper bound of density, and by finiteness of k by k tilings, you should be able to get a least dense tiling just by enumerating. Yes, however, the question is like, what about like a k plus 1 by k plus 1 tiling? Is it possible that you could do better than a k by k tiling? Yeah, so maybe to word this a little bit more explicitly, there is a k by k square tiling which minimizes density across the set of all possible tilings or aperiodic patterns that are not tilings. Can you reach optimality when restricted to k by k? That's the question. There's an optimum if you like. There's an optimum among the set of k by k tilings, but like, is one of those optima globally optimal? So that's the question that I'm asking here. Okay, so at this point, I'll say this is as far as I got when it came to like proving things by hand. Yeah, is the optimal for k by k necessarily optimal for the whole thing? That's the question, correct. Okay, so then forget about all that. Let's try some search, because at that point, I was not really sure where to go. And to be clear, when I started this problem, I was thinking about connect 4. I was thinking about the 4 connectivity on a diagonal case, and the best I was able to get by hand was like 6 tiles out of 16 on a 4x4 grid. So can you do better than that? Question mark. And I was never able to like prove that there was a better result, or I thought I did at one point, but then it turned out it was wrong. So let's just try some search, right? And this was a good opportunity. I'd known about like ILP for a while, and I'd never bothered to solve something with it, but this seemed like a good time to try it. So that was just my tool of choice, not necessarily because I knew it was the best for the job, but more so because I wanted to try it. It actually turned out being just fine. So in case anybody is not aware, what ILP is you have a bunch of constraints among integer variables. So in this case, it would be these here. So like each of these is just some inequality on like some linear equation across like integer variables, and we're trying to maximize some other variable, which is also restricted to be an integer. And this turns out to be NP hard, so it's very slow to be solved. However, fortunately, a lot of people have worked very hard at making this good enough in practice. So there are some pretty fast ILP solvers out there. So integer linear programming. ILP is integer linear programming. There is also like separately linear programming and integer programming, where you remove some of the conditions on what I've just described, where maybe these formulas are not necessarily linear, or whether your variables are not necessarily integers. But we're concerned with an ILP question because effectively we have like a 2D array of zeros and ones. You can think of it as unblocked cells and blocking cells. And like lines of length k have to sum to at least 1 within that 2D array, right? So if we take a length k line, which is the connectivity of our game that we're playing, then like you have to have at least 1 block in there. The thing that you're trying to optimize for is the sum of the entire array, and at that point you just throw it at some ILP solver, and I just used the one in NumPy because that was the only one I bothered to try, not for any good reason. Okay, and so sure enough, this is the hexagonal case, and you'll immediately see an interesting pattern here. Anybody see what it is? Unmute. Somebody unmute. I feel lonely. Odd numbers, yeah.
It just round up to the nearest odd number.
Right, exactly. Yeah, so we have this like 1, 3, 3, 5, 5 thing going on. So, okay, we did already prove before that like the odd numbers themselves were optimal. So this at least matches our expectation here. And to be clear, what this pattern is showing here is like we're going along with the assumption in our conjecture a minute ago, where there's a square, like a k by k square tiling, which minimizes density. So like we are treating like for length 9 here, what I'm saying is k equals 9, and we have a 9 by 9 box, and there's 9 walls was the optimal amount of walls that you had to place inside of it. And sure enough, that that matches what we.
Are you muted? I can't. I suddenly can't hear you.
Test. Sound check.
I can hear fine.
I can hear you.
Okay, good. Can you hear them?
Oh, there it is.
Okay, cool. So yeah, this matches our expectation. The only thing here that does not match our expectation is, or at least so far, is length 2. So this is a 4 by 4 square, or rather like hexagonal diamond being tiled that has 3 walls filled. And as we showed a minute ago, we can do better. That's 3/4 density, whereas we achieved 2/3. So that's the one contradiction to our conjecture that we've mentioned so far. So what about the rest of them? I'll leave that hanging for a minute. I won't answer that question now. Hint, hint, partially because I don't know the answer. But here are some of the patterns. I'll maybe just give it a sec if people want to stare at those for a minute. You'll see that, in each case, like in the odd ones, you'll see that in this case you can indeed do a knight's move for all of the odds. Remember earlier our proof was concerned with the 8 connectivity, but now we're doing hexagonal connectivity. So those will actually work here. And is that true? Yeah, that is true. Yeah, you can always do the diagonals, which is equivalent to like the thing I showed above, where there's like 2 like alternating lines. I guess it's just like a sort of rotation and a shift of perspective, and that looks like a knight move. So okay, I'm gonna move on. So that's
before you do.
Yeah.
How big roughly did your solver only like find one solution?
I don't know.
For each of these? Okay.
Well, yeah, the solver only found one solution, but that's not to say. But that's because I think the way I defined it was that it would just break out as soon as it did find one solution. So it wasn't going around looking for more minima. I would assume for each of these, there's probably a lot of them. Because I can necessarily say that for number 9, because as we just mentioned, the knight's move should work for any odd number, but this is, this here is 1/9, and sure enough, it's not doing the knight's move, so that's at least 2 for that case. Cool. Any more questions before I show you my results for the 8 connectivity? Some people typing.
I find it pretty interesting both that the optimum of 1/k is attained for the odd case, but also that it doesn't seem to be for the even case. I think both of those are pretty interesting observations.
You mean to say you're expecting that you would be able to get a tight solution that only uses 8?
Yeah, it seems that if you just kind of shuffled around the things in each row and each column, that maybe you could get 1/k unconditionally, but apparently you can't.
Nope.
That's kind of weird.
No, yeah, you can't. Anybody have any predictions for what the next one will look like, based on what we've observed here? Anything? Any possible commentary that you can make on the next the diagonal? Yeah.
I would hope that we also get 1/k in at least some proportion of the cases. That's my expectation.
Okay, well, we did say the primes, but unfortunately that's not really a proportion. But I think if we using the
asymptotic density, that's my
right,
conjecture.
Right. Yeah, but using what DUN said earlier is yeah, exactly, coprime to 6. If coprime to 6 is correct, which I haven't really confirmed to myself, then that would indeed be a positive proportion of things that would satisfy the property of being exactly 1/k. However, we should also expect this should here be a lower bound also, right? We should expect it to be bounded below by this, because we have the same type of connectivity, just with one more diagonal of connection added, right? Okay, so what do we get? I couldn't really go quite as high because I think I actually hit 21 after maybe 21 or 23 or 24 or something after I took the screenshot, and the pattern did continue. But in 8 connectivity, there's more constraints that I have to place on it, so it goes a little slower, and I only got up to 15. But there's some interesting stuff going on here, right? This does not seem quite as patterned as the hexagonal case. So what's up with that? For example, you'll notice here between 12 and 13, it actually decreases in the amount of walls that are necessary. I'll leave it to you to convince yourself that that's not fundamentally impossible or anything. It's not. The same happens between 4 and 5, and also 6 and 7. So that's curious. Also, there's no pattern seemingly here. But I'll go ahead and drop some points, drop some values here. Why would it decrease? Doesn't k+1 connectivity imply k connectivity? That's a great question. Anybody have an answer? I know the answer, but I'll leave it as a puzzle. Ooh, is our conjecture from earlier wrong? Uh-oh. Unless I'm getting the table wrong, the table looks wrong. Sorry, I'm failing to parse that sentence. What do you mean? Unless I'm getting the table wrong, the table looks wrong. You probably are getting the table wrong. Yeah, this is for squares. Yeah, so this was for hex grids. Where yeah, so This is for hexagonal connectivity where we have the odd, like ceiling of odd pattern, and this is 8 connectivity, or like squares with both diagonals. Any answers for why it wouldn't decrease? Every number in the... Yes. Yeah?
Longer rows are easier to block, so it's not necessarily strange that the sequence is non-monotonic.
Yeah.
It's just harder to justify why that would be the case.
Right. Yes, this is all 8 connectivity. Every number in the 8 connectivity case is at least as large as in the 6 table. Yeah, that should be the case. And I think
And if it is the case that your conjecture from earlier is wrong with probability greater than 0, then this could also be an artifact of using k by k grids.
Yep. Okay, so coming back to the conjecture then, one thing you'll notice here is, check out this. So I've wrote the amount of walls here, but I've also wrote the densities of the tilings. And you'll notice here that the densities are also non-monotonically increasing. So it's specifically in this case, so we go from 0.2 to 0.2222222 between like the blocking a length 5 connection and a length 6 connection case. So in other words, tiling this 5x5 pattern is actually better than tiling the optimal 6x6 tile when solving the 6x6 case. Does that track for everybody? Maybe not intuitively, but like, does it make sense that that's not like universe breaking? Yeah. So, okay, that's interesting. The 5x5 square, which blocks length 5 connections, is less dense than the 6x6 square, which blocks length 6 connections. Yeah, anytime you see the night grid appear, it has to be good for something. Okay, so the conjecture is false. And as I mentioned before, another counterexample would be this tiling from earlier. Okay, so we've got some counterexamples to our conjecture. For lengths greater than 8, shouldn't there be at least 2 walls per line? For what K and what graph type or what grid type? For lengths greater than 8. Are we talking about this? For lengths greater than 8, shouldn't there be at least 2 walls per line? We're not talking. This is connectivity 8 and block size 8, because we're kind of implicitly thinking here about the conjecture. Oh, okay. Bye. Yeah, we're still implicitly thinking about the conjecture here for we're assuming that the grid size and the connection size should match, but as we've now shown that's not the case. I think that's hopefully answers DUN's question, but I think he already left. Okay, so new conjecture. Is there some tiling which has dimensions greater than k and is better than all tilings with dimensions less than or equal to k, for k is greater than 2? So in other words, is the tiling, like in the case of this tiling here, it was smaller than the 6x6 tiling. Is it ever the case that we have a bigger than 6x6 grid? That, like, for example, like, you know, maybe there's some like, maybe for 23, it turns out the optimal tiling that you can get actually involves using like a width 28 by 28 box. Actually, that's a bad example because once again, it's prime, but you get the idea. Yeah, the K2 hex pattern was also like that, correct? But aside from that edge case, anybody want to do a poll? Sorry, I'm taking a swig of some water. Thank you for organizing the polls.
Just to be clear, a positive answer means that yes, we believe there is another such counterexample.
A positive answer means you think, sure, we can do it that way. I think I said the opposite way around. Oh, no. Sorry. Yeah, you got it right. Yes, a positive answer is to say that there is another counterexample. Okay, so I guess MathSpin thinks there's a couple. I think we're 3 people think there's no counterexample, and 1 person thinks there is a counterexample. Fractal is thinking about preemptive blocking on the hex grid. I think the poll just flipped around from 1 to 3 to now 3 to 2. Okay, so some people changed their minds. All right, so I don't have any brilliant intuitions here, so I just decided to do some search. So in both cases of the hexagon grid and the diagonal grid, let's just go ahead and like try really big grids and see if we can do better. And I'm calling these unicorns for lack of a better term. So for the diagonal grid, ooh, we got a couple counterexamples. So this was my favorite. This was the most interesting of them for me. So this is a 6x9 grid for L equals 4, or sorry, this is K equals 4. And this does ever so slightly better than the optimal solution for you can imagine. I don't know why I called it L. I think it was like length or something. This should be like it's the K that we've been talking about. For connectivity of if you do a 4x4 thing, you get 0.375, I think, if I'm not mistaken, which is 6 out of 16 blocks. But with this 9x6 grid, you get 20 out of 54. Which is ever so slightly better. Now, as we already saw, this isn't necessarily a counterexample to the Newark conjecture, but it's also an interesting case of the Knights pattern working for L equals 6. It turns out the Knights pattern actually beats out the 8x8 pattern too. So you get these Knights moves on a 7x7 grid, which works better for tiling and connectivity 8 pattern. And also there's this interesting little tiny case for if you're trying to avoid length 3 connections. This 2x4 one works just fine. And I think that beats, I think that ever so slightly. Let me check. What was the... Yeah, so we used 5 walls in a 3x3 grid in this pattern, which is ever so slightly more than half. But using this 2x4 one, you can do better. Okay, so what about the hexagon grid? Anyone want to take a poll on the hexagon grid? Do you think there will be any quote unquote unicorns aside from the 2x2, sorry, the 2 length 2 case? Everyone's voting thumbs up for unicorns because I've beaten it into all of your minds that this is a weird problem at this point. And just when it couldn't get any weirder, I found none. I found no unicorns in hexagon land other than the 2x2, the length 2 connection. Now, some part of me wants to believe that maybe that has some kind of connection to the fact that, in the case of hexagons, we saw that very clean, even, odd pattern. So I feel like there's definitely something to be proven there. But evidently it's much more complicated with with this pattern here, 1 3 5 6 5 blah blah blah. Who knows what's going on there? So maybe this is really the only one for hexagons. I was not able to identify any others. That's not to say they don't exist, but I couldn't find any through search. Where did I go? Okay, so that's pretty much the end of my actual results that I've found so far. So that leaves a question. Is there an aperiodic anticonnective non-tiling which beats all periodic tilings? And what I mean by that is like there's some like random pattern that doesn't actually tile. It's not repetitive necessarily or periodic. Can I get a poll on that just for funsies? Strictly beats question mark. What do you mean by strict? I'm not saying strictly. So I'm saying, you know, does the existence of a density D random looking pattern imply the existence of a density D tiling or better? No one's voting.
What do I vote if I believe that you can tie a periodic tiling with an aperiodic one, but you can't beat it?
That would be a thumbs up, I think.
You kind of reversed it. If an aperiodic tiling implies a periodic one, then that means you can't beat it. You can't beat the periodic one.
So to phrase it in more emotional terms, I'll rephrase the question as, can we be optimistic that we don't ever have to like consider like bizarre patterns that are not tilings when looking for the optimal solutions? So the thumbs up would be the optimistic case of we can just deal with tilings forever. Okay, lots of thumbs up. Okay, I'm also a thumbs up on that question. I don't have a proof. What I can prove, yeah, so my conjecture is no, which is a thumbs up. So given such a tiling, here's what we can prove. We can prove that the best tiled density that's achievable is at the infimum of. Am I saying that backwards? Yeah, the best tiling density is at the infimum of all. No, I'm saying this backwards, aren't I? The best bizarre non-periodic tiling is at the infimum of the set of possible densities that are achievable by periodic tilings. So a brief proof of that is if we do have a tiling that has density D, that is to say like a non, sorry, I say tiling, I should really say, given such a pattern, a non-tiling pattern that has density D, if just choosing some epsilon greater than 0, you just, we're going to construct a periodic tiling that has density less than D plus epsilon, and the basic idea is that you just cut out a big block of the aperiodic tiling, fill its perimeter, and as the block gets very large, the perimeter is vanishingly small compared to the area of the whole tiling, and then you just tile that. Yeah, exactly. So yeah, same as what Violeta said in the chat. So I think that's all of my slides. Yeah, that's all I got. Any questions? I'm reminded, I forgot to write this in when I was making the slides today. I think someone, will the slides be posted? I guess I can post the slides. I don't usually do that. I'll post a recording. But yeah, I could try and like export this as a PDF, assuming it doesn't give me too much hassle. One thing I didn't mention, I think someone found a construction for the way to generate these the tilings in the hexagonal case that requires just one more, and it basically uses Knight's moves and like one extra piece that is carefully placed, and I forgot to include that in the slides. To be clear, a lot of this was discussed in WebGoat Guy's server, because that's where people have been playing the Connect 6 on a hex grid. So this was something that I had been thinking about, and then people prompted me to think about it much harder just recently, and that's what prompted this talk. But yeah, any further questions? Did you mention why 1 over n is impossible for n connectivity on a hex grid for even n? Is that proven? If that was proven, I don't remember the answer or the reason. You showed it earlier. Okay, what's tell us, what is the proof?
Yeah. So I think like in WebGoat server I kind of mentioned it, but basically it's like if you have like the two axes be like 60 degrees apart, and you basically label the rows and the columns, you just index them from like 1 to n or 0 to n minus 1, and you basically like and when you mark n cells, you just take the sum of the rows and the columns of like each cell. So because you picked one cell from each row, one cell for each column, the sum should be the sum of all the indices of the rows and the columns. But if you want to look at the diagonals as well, the diagonals have like a fixed sum. So basically what happens is that like, I think it would have to be congruent to like it has to be congruent to n times n plus 1 over 2 mod n. But when you do the sums of the rows and columns, it doesn't match. And this is for even n specifically.
Okay, that's interesting. To be honest with you, I was not able to follow all that, but
Okay.
yeah, maybe
I'll
if you have
share
like a
diagram.
graphic, that would be awesome.
Yeah, sure.
So I guess there's some like it sounds like that, like you're actually adding numerically the coordinates. Is that did I get that right? And like there's
Yeah, I'm
some
adding the
contradiction
coordinates.
that you.
So
Okay.
each diagonal is like a specific sum,
Mhm.
but because you have a cell in each row and each column, you actually know exactly what the sum is. And to satisfy the diagonals, you need to like satisfy something like mod n, but it's not satisfied. It's just you just can't satisfy it with
Oh, cool.
even n.
Interesting. Yeah.
Wait a sec. So I think that the argument that you're saying essentially proves that you can't have like an n by n section where all of the rows and diagonals and columns have like one piece in them. Does that
Yeah,
also
basically
mean that
that.
does that also mean that like the density of the entire thing can't be 1 over n? Like we already know that like
Yeah.
these like repeating sections don't have to be like of size n times n necessarily.
Yeah, but I think if it's exactly 1 over n, then it would have to be possible on an n by n grid.
Oh
Like
yeah,
for
actually
like the
that does
strict
make
lower
sense.
bound.
Yeah.
Yeah, I think the proof, just to lay it out a little bit more explicitly, I think the proof for that would be on each row you would necessarily be skipping like the vast majority of the time you would be skipping like 5 cells. In the case of, we'll say in the case of k equals 6, just for simplicity, you'd be skipping 5 cells in between your two blockers. So that implies like a horizontal period of length 6, and then like equivalently you get a vertical period of length 6. So you can construct the period given the.
Yeah, not just in the vast majority of cases, but in every case, right? It's forced, and that's why it's periodic.
Well, no, because you can have a density, like a density 1 over n tiling that has like an individual impure cell. Like you can just tile like put one extra piece in, and that would be like, that.
Right.
So
Okay.
there would be like,
Yeah.
Yeah, but like every like n times n section would have to have like n plus 1 pieces in them, right? So like your density has to be at the very least like n plus 1 over n squared, I think.
n plus 1 over n squared.
I think that's what the argument is saying. I might be misunderstanding.
Actually, yeah, I think that's right. Right, because if the density was. Yeah. Wait, is that a proof of optimality then? I think that's right? If so, just to
I think it is.
clear up my
It's
understanding.
hard to do math on the fly, but I think it is.
Yeah. So like if you have a density that is any less than like the 1 over like the, what's it called? I'm just gonna go back to the table here. If you have any density that is like any less than this value that is shown on this like even odd pattern, then that would imply the existence of at least one like small area within it that has like a 6x6 tiling that would then tile and get you down to a
Wait,
perfect.
but for length 2, isn't like for hexagons, we already know it's 2/3,
Right. I
which
think
is smaller
yeah.
than 3/4.
I think that then comes back to your original proof of adding up the columns. I think you would have to have an edge case in that proof. I think that's why this is a problem
No,
there.
my proof is only for like n by n specifically. I wasn't considering like other sizes.
Right,
So
right,
for
but
like,
And only for even n, you said, right?
I mean, yeah, but in this case, n is even. N is 2 here. I was just showing that for even n, it's impossible to get n cells, n walls on an n by n grid. But for
oh,
length 2, the more optimal solution was not 2 by 2. It was 3 by 3.
So basically, all that remains in the hexagonal case is to find the actual way to tile the hexagon to get these bounds, right? Assuming that they're in fact true. That's all that remains.
yeah, and uh, I'm not sure I know how to rectify that with what DUN just said, but but that matches my intuition, if not what I know for sure. But I'm pretty sure I think someone, what I was mentioning a minute ago is I think someone has actually constructed this, the general case of how to construct
so the
the
hexagon problem is solved. Awesome.
if we yeah, as DUN saying in chat, I proved that for even n you can't have n walls on an n by n hexagon grid. So that's not to say that
Yeah.
the counterexample is that for n equals 2 there's a better solution in 3 by 3. Wait, I'm lost. I've confused myself at this point.
Like the counterexample for n equals 2, the 2/3
Yes.
wall solution, that's a 3 by 3 solution.
Right.
So it's not
Yeah.
actually a counterexample to what you proved.
Yeah,
it's a
that's why I put
counterexample
in
to something
quotes.
else.
It's not actually a counterexample. Sorry.
Oh, okay.
if that
So
was
we're good.
Yeah, but the thing that I'm saying is that if I'm understanding this conversation correct, we already know that in the odd case, the asymptotic density is at least 1 over n, and in the even case, it's at least n plus 1 over n squared. So all we need to do is find actual ways to tile the board which achieves that density, and then we're done, right?
I think so, but yeah, I think so, and I think that has been done.
Yeah, so that's what I'm saying. I think the hex. I mean.
Yeah, you might be right. I'm
Yeah.
I'm just trying to my brain is overclocked right now, so.
Yeah, sorry. This
No, you're good.
This is my. All I know about this problem I've learned in the past hours, so
Right.
maybe don't take me too seriously.
I think you're right though. I don't. Yeah, I'm not yet seeing the issue with it, other than just
so what's
the
solved
confusion
is
around this.
the on a k by k grid, or is it in general solved? What do you mean?
On a. I think it sounds like we're saying it's solved in general. The hexagon case is necessarily this density as we increase.
But it's not only it's on a k by k grid, but we already saw the k equals 2 counterexample. This time it would actually be a counterexample, right?
I thought the idea there was that if we have a a larger pattern, then you could take a subsection of it, and the presence of a tiling that is lesser density than the greater odd value would then be that would then imply that pattern could then be tiled across the grid, and then you would arrive at a tiling equal to 1 over k. Although I'm not sure that holds. n grids work there. Yeah, honestly, I need to write it out. I don't know for sure. Yeah, to put it in hyperbolic space. Yeah, what it was. like pentagonal tilings or something. That would be fun. Yeah, so like one other thing that I didn't mention here is like, you can of course generalize the what's it called? You can generalize the connectivity types. Like there's nothing stopping you from considering more exotic graphs than these two types of connectivity or these three types of connectivity. Yeah, connectivity types today are grid confined. You can also like consider like hypergraphs where like we're concerned with, I don't know, maybe like a 3x3 box being like tileable, or like counting as a solution, right? Like if you make like a 3x3 box anywhere in the grid, at that point it seems to just like generalize to some sort of packing problem or something. Yeah, I don't know. Going the other way, can we find a solution from the triangular tiling that we can then generalize using some method to the hex tiling? Triangular tiling means like, by that do you mean like we have a triangular grid as opposed to a grid of hexagons? Ah. But you can't even make a straight line on a triangular grid, can you? Like, it doesn't quite work in the same way. Yeah. Yeah, as DUN says, how do you define a line with polygons with odd number of sides? Right, because if you like start making a line, well, I guess it could be like, I wish I had triangles to point at. I think either you have to basically make it into a hexagon grid where you're like, each triangle can like start making a line at the same diagonals that a hexagon grid would allow, in which case it's just the same as the hexagon problem. But no, actually maybe that's not true. I don't know. Yeah, I think maybe you can do it. Yeah. But is that not the same as hexagon tiling? I'm gonna. You don't think so?
I mean,
if you drew the hexagon grid on top of that grid, it would be a zigzag hexagonal column.
Oh, would it? Oh, interesting. Huh. I guess
because
so, yeah.
every three triangles on that line is half of a hexagon, but it sticks out in opposite directions.
Right. Interesting. I have no idea how it would work on that one. Cool. Any other questions? Good ideas, interesting ideas I don't have the answers to.
We could generalize this line on polygons with with odd number of sides by going alternately left and right on the opposite side of the polygon, basically. Not sure if that came across, but
well, on other odd polygons, how are you even like tiling the grid? Are we assuming hyperbolic space here?
Good question. Yeah, I don't know.
Okay.
But yeah, in hyperbolic space, I guess.
Yeah. Okay. Yeah, probably. I mean, that could possibly work. Yeah. Anyway, I mean, I feel like the answer to this question is just there is no quick trick. Like it seems to me from staring at these, like this thing here, most of all, like there might not be some nice general formula for all of these problems. It seems like it's just kind of like another packing problem where You just kind of have to solve things with search or something. Yeah, blocking a specific polyomino, yeah. Definitely seems in the same class of problems. You can generalize to any graph if you give a predicate for determining whether a vertex set is a line. Yep, yeah. Are tilings even the best way to conceptualize this? I want to play on an E8 lattice. Yeah. Yeah, you can certainly do this on like all sorts of bizarre and exotic graphs or hypergraphs or weird structures and stuff. Okay, if no more questions, I'm going to stop the recording. Cool, cool, cool. Thanks everybody for coming.
Thanks for giving the talk.
Absolutely.